Okay, so then we have 1 times 30, right? Because it's 20 and 1. And 1 times 30 is 30. Okay. And this is 20 times 6, right? This one was 36. So 20 times 6 is what? 120. And then we have 1 times 6, which is? Okay, and so now again we have 4 partial products that we need to add. So 600 plus 120 is 720 plus 30, 750 plus 6 is 756, and now we have shown that 21 times 36 is equal to 756. And that is super, super exciting, isn't it?
So if we did that using, right, if it was decimals, it would be tricky.
No, because it would be 6.
I don't think I understood when you said that if we times a decimal by a decimal using the set model. Is that what you said, or?
No, this is area model.
Area model.
Yeah.
Oh, okay.
So this would work quite nicely with decimals because I'd have 2 decimal 1 and 3 decimal 6. So I get 6, 1 decimal 2, 0 decimal 3, and 0 decimal 06. So my answer would be 7 decimal 56.
Okay, I got the model.
Okay. This also works if you're multiplying 3-digit numbers. Okay. Let's just for the sake of fun. You want to see something cool? Not that you would ask kids to do this often. And don't expect these to be drawn to scale, but if I had 125 on one side and 326 on the other side, 100 times 300, you know what that is?
300.
How about 1 times 3 times 100 times 100? How many zeros do I need? 4. Sure is. 20 times 100? 2,000. 6 times 100?
600.
20 times 300? 6,000. 20 times 20? 400. 5 times 300? 1,500. 5 times 20? 100. 6 times 20? 120. 6 times 5 is?
You would never
30.
ask the elementary school student to do this over loud.
You notice how your place values line up on diagonals?
Oh.
Okay? So I've got 38,000, 39,000, 40,000, 500, 600, 720, 750. 40,000. What did I say? Can't remember what I said now. 750. Okay? So the strategy expands to larger numbers. Right? It's actually a very commonly used mental math strategy. It also expands to multiplying polynomials together, which if you really want to see that, ask me after. multiply like x squared plus 3x plus 7 times x squared plus 2x plus 5, I could do it the same way. Okay? So the area model is very much our friend, and it's never gonna let us down, really. But the whole thing about the area model is it's broken into partial products, which are all based on the distributive properties, right? So this is really just applying the distributive property and breaking it into the parts, multiplying each part by each other part, and then adding them back together again. Okay? And it's, in my opinion, a lot easier than lining them up and talking about carrying and moving and putting down zeros because I said so and stuff like that. Okay? So we want kids to have the opportunity to think about multiplication using the area model. I actually am a big advocate of kind of never really teaching any traditional algorithms for multi-digit multiplication because most of them don't make sense to kids. So as I asked you, can you make me an area that's 12 by 13? Most kids will be able to do that, and then they'll develop a strategy for multi-digit multiplication from that. But today we're going to move on from what we learned about multiplication, and we're going to talk division. Now you remember last day I talked about division, kind of he's like a superhero, right? Why did I say he was like a superhero?
Groups of different, what did you say? It breaks things into groups of certain number or certain amounts, or it breaks things into a certain number of groups.
Right on. So division is a superhero because it has a double identity. It can do two things. Right? So if we think about the set model, I break an amount B into A groups. So I take 12 and I break it into 3 equal groups. That's one way to think about the set model. Okay? And I wonder how many are in each group. The other way to think about it is I take 12 and I break it into groups of 3. So groups of a certain size. Okay? So this would be I take 12 and I break it into 3 equal groups. This one would be I take 12 and I break it into groups of 3. Okay? Same thing with the area model. I have an area, let's say 12 square units, and I'm going to show you some examples about this in a second. And I organize it into rows, right? So I have 3 rows. Well, how much is in each row? Right? I might ask you that. Or I have 12. I break it into rows of 3, so I put 3 in each row. How many rows do I need? There's 2 different questions that I could ask. And the different questions will generate different models. Okay? Same with the linear model. I have a length that is a certain length, and I break it into pieces that are a certain length long. How many of those pieces do I need? Or I have a certain length, and I want to break it into so many equal pieces. How long are the pieces? Okay? So regardless of what model you're using, you always have that double nature for division. And sometimes kids can get confused. And you'll remember that when we learned about addition and subtraction, we talked about structures of story problems, and sometimes there were things that were missing, right? It's the same with multiplication and division. There are different structures of story problems. And we want to create story problems that get kids thinking about all of these different models. So ones that will make them think linear, ones that will make them think set, ones that will make them think area, ones that will make them think about one mode of division, right, the fair sharing, versus the other mode of division, which is the partitioning or equal subtraction. Okay? And again, we want sometimes to give them ones where there's missing values and all that kind of fun stuff. Okay? So let's just look at a model. So again, if I'm talking about 12 divided by 3 as my question, with a set model, that might mean take 12 squares and put them in 3 equal sets. So kids will start doing things like fair sharing, right? Like, oh, I give you some, and I give you some, and I give you some. Oh, I still have some more. Okay. Well, I'm going to give you one. I'm going to give you one. I'm going to give you one. Oh, I can still have enough more to give everybody one. Right? So this is the notion of fair sharing. Okay? So 12 divided by 3. Put 12 in 3 equal groups. How much is in each group? And how much is in each group?
4.
4. Right. Okay? The other way I can think about it is I have 12 things and I want to make groups of 3. So I might be like putting bags together where there's 3 candies in each bag, right? So in this case, I know that my set size has to be 3. And what I want to know is how many sets can I make, right? So in this case, I have 12 candies. I want to put 3 candies in each bag. How many bags can I make? So I'm looking for the set size or the number of bags. In the other one, I might have 3 bags and I want to put the same number of candies in each one. Okay? But either way, you get the answer of 4, right? Now, one of the things that we want kids to think about, though, is do they model the situation they've been given, right? So when we give them a story problem, are they making their models correctly? Because sometimes kids will draw the other model for the story problem. So you really want to make sure their model and their story connect. So 2 ways to show a set model. 12 divided by 3 means break it into 3 equal groups. Right? Let's break that up here. So this version is break it into 3 equal groups. The other one is break it into groups of 3. Okay, so one is break it into 3 equal groups. How much is in each group? The other one is break it into groups of 3. How many groups do you have? Okay, if I wanted to do that with an area model, I might say, okay, take 12 and make it 3 rows high. How much would go in each row? So I'm fixing the height to be 3 and my area has to be 12. Okay, so how much is in each row? You see the other dimension is 4, right? The same thing could be asked, oh, don't crash, don't crash, don't crash.